Hello students. So in the previous video we discussed about convolution integral and we derived the general expression for convolution integral. In this video we will be discussing properties of convolution integral. We have three properties in convolution integral similar to the convolution sum. Those are commutative property, associative property and distributive property. So let's take one by one and we go through the proof of each property here. So we'll start with the commutative property. Okay. So the statement or the commutative property definition says x of t convolved with h of t is equal to h of t convolved with x of t. So let's take the proof for this. So we start with the LHS. So from the definition of convolution integral, x of t convolved with h of t is equal to integral of, so the limit is applied to tau. So tau is equal to minus infinity to plus infinity x of tau h of t minus tau d tau. Call this as equation 1. So now I will replace this t minus tau with some other variable. So put t minus tau is equal to lambda. So t minus tau is equal to lambda. Then what happens to this tau? I have to replace tau with the respective variables. So tau will be equal to t minus lambda here. Okay, and d tau will be equal to minus d lambda. Okay, since I am replacing this tau with t minus tau, so this tau d tau will become minus d lambda, and this limit tau varying from minus infinity to plus infinity. So let's see what happens to this. So tau is equal to t minus lambda. So t minus lambda is equal to minus infinity. So minus lambda is equal to minus infinity minus t. So if you multiply by minus, you will get lambda is equal to plus infinity plus t. So that means anything added or subtracted with infinity, you will get infinity itself. So therefore lambda is equal to plus infinity. So that means the lower limit becomes plus infinity. In the same way, the upper limit will become, this become minus infinity and this become plus infinity. So let's apply all these changes to equation 1 and replace the respective variables. Okay. So then what happens to equation 1? So equation 1 will become integral lambda is equal to plus infinity to minus infinity, and this x of t minus lambda h of lambda minus d lambda. Okay. So let's take a minus outside here. Lambda is equal to plus infinity to minus infinity x of t minus lambda h of lambda d lambda. Okay. So if you vary the limit, if you interchange the limit here, plus infinity to minus infinity is there. So if I interchange that, so this minus can be eliminated. So then what happens to this? So lambda is equal to minus infinity to plus infinity h of lambda x of t minus lambda d lambda. And to the LHS, we started with x of t convolved with h of t. So this is what we get, and now we can include one more step by replacing this dummy variable lambda with tau. So that gives you h of tau x of t minus tau d tau, which will be similar to the expression of convolution integral, and or you can skip that step or directly compare this with the expression of convolution integral, and directly can write this as h of t convolved with x of t, x of t convolved with h of t is equal to h of t convolved with x of t. So that completes the proof of this commutative property. Now you can verify this. We have the same limit lambda, h of lambda, x of t minus lambda, d lambda. You can have a look at the expression tau, x of tau, h of t minus tau, d tau. So similar to the expression of convolution integral. So you can write it in this way. Hence the commutative property is proved here. So let's take the next one, that is associative property. So the associative property says, the definition says x of t convolved with h1 of t whole convolved with h2 of t is equal to x of t convolved with h1 of t convolved with h2 of t. So this is the statement of associative property. So let's take the proof of this. So I will define these two terms with some other variable. Let f1 of t is equal to x of t convolved with h1 of t, and f2 of t is equal to h1 of t convolved with h2 of t. Okay. So call this as equation 1 and call this as equation number 2. So from the definition of convolution sum, I can write f1 of t is equal to integral tau equals minus infinity to plus infinity x of tau h1 of t minus tau d tau. So give it a number, equation 3. So then what happens to with from in the statement, we start with the LHS here, x of t convolved with h1 of t or convolved with h2 of t. So that is equal to f1 of t convolved with h2 of t. So this will be is equal to f1 of t. I am replacing this entire term with f1 of t, and h2 of t is kept as it is. Now let's define the right hand side of the expression. I will need some space here, so I'll start from here. Integral of, since I am using tau here, in equation 3 I use it tau. I will use some other variable called sigma is equal to minus infinity to plus infinity. f1 of t is there, so this becomes f1 of sigma h2 of t minus sigma d sigma. Okay. Now we have f1 of t expressed here. Then we can substitute the equation 3 here in f1 of sigma. The only change is this is f1 of t that gives us t minus tau. Here it is f1 of sigma. That means to replace this t with sigma to make this happen convenient. Okay. Let's do that. So integral minus sigma is equal to minus infinity to plus infinity. So f1 of sigma is tau varying from minus infinity to plus infinity, x of tau h1 of sigma minus tau d tau, and we left with h2 of t minus sigma d sigma. So this is what we get after substituting f1 of sigma here. Now in this, let's interchange this term with some other variable. Put lambda is equal to sigma minus tau. Then I have sigma here to define with. So then what happens to sigma? Sigma is equal to lambda plus tau, and here this limit sigma will changes from lambda, because as I discussed, shown in the previous one, lambda plus tau is equal to minus infinity, lambda is equal to minus infinity minus tau. So that means lambda is equal to minus infinity itself. So this limit changes to lambda from sigma. Okay, and wherever you have, we have this sigma minus tau is replaced by lambda here. So let's see what happens to the expression. If you change this, then this term with respect to tau will become constant. So better we interchange this integration with this, so that it will be convenient. This will become lambda and this will become lambda. So this will be convenient for us to simplify the next step. So we take like this. Put lambda is equal to sigma minus t, and interchange the order of integration. So we change the order of integration. So let's see what happens to the expression here. So this will give us integral tau varying from minus infinity to plus infinity x of tau, and this will be lambda varying from minus infinity to plus infinity h1 of lambda. So this h1 of lambda is there. Now observe this h2 of t minus lambda is there. So we have to t minus sigma is there. So we have to substitute this sigma lambda minus lambda plus tau here. So that becomes h2 t minus of lambda plus tau. Okay. So then what happens to our integration term d lambda, and then this whole term d tau. Okay, so this d tau I have kept outside. This d sigma will become d lambda. As I have interchanged this, I am keeping this tau outside the integral of this term. Now just simplify this. We have to multiply this with minus integral tau is equal to minus infinity to plus infinity x of tau, and here integral of lambda is equal to minus infinity to plus infinity h1 of lambda h2 of t minus, I will write tau first and then I will write lambda for my convenience, d lambda d tau. So now give a equation number for this. We have 3 here, and give it a name, equation 4. Okay. So let's go back here. We have f2 of t, which is defined as h1 of t convolved with h2 of t. Now express this. I'll use lambda here. It will be easy for simplification. So lambda varying from minus infinity to plus infinity, h1 of lambda h2 of t minus lambda d lambda. So the integration variable here I'll take lambda. Since the system possess linearity and time invariant property, so we can write it like this. See, if f2 of t gives the expression like this. So what if I use the time invariance property and give the input f2 of t minus tau. So if f2 of t gives the expression in this way, then f of t minus tau uh, will provide us the equation in this form: h1 of lambda h2 of t minus lambda t minus tau minus lambda d lambda. Okay, now if you go to equation number 4, you can see this entire term. We have the same limit lambda varying from minus infinity to plus infinity. We have h1 of lambda here, h2 of t minus tau minus lambda, same thing, and d lambda. So that means this entire term I can replace with f2 of t minus tau from whatever we assumed in the beginning. Therefore, equation 4 becomes, so what happens to equation 4? Equation 4, we can simply write it like this: tau is equal to minus infinity to plus infinity. We had x of tau, and this entire term in equation 4 is replaced with f2 of t minus tau d tau. Okay. So now this term I can write it in this way from the definition, comparing this with the convolution integral definition expression. I can write less x of t convolved with f2 of t, and to the RHS what we have, x of t convolved with h1 of t whole convolved with h2 of t. Now what is f2 of t? We have defined it as h1 of t convolved with h2 of t. Let's substitute here the value of f2 of t from equation 2, comma, we get x of t convolved with h1 of t convolved with h2 of t is equal to, now I will substitute f2 of t here, so that gives us x of t convolved with h1 of t convolved with h2 of t. So this completes the proof of associative property. So let's move on to the next one, that is distributive property. The definition of the distributive property states like this: x of t convolved with h1 of t plus h2 of t is equal to x of t convolved with h1 of t plus x of t convolved with h2 of t. Okay. So let's start with the LHS proof of this. So x of t convolved with h1 of t plus h2 of t. So from the definition of convolution integral, so you can write it like this: tau varying from minus infinity to plus infinity, x of tau h1 of t minus tau plus h2 of t minus tau d tau. So let's go for further simplification. Tau is equal to minus infinity to plus infinity, x of tau h1 of t minus tau d tau plus integral of tau is equal to minus infinity to plus infinity, x of tau h2 of t minus tau d tau. Now compare this to expression with the definition of convolution integral. We can write it as x of t convolved with h1 of t, and this one as x of t convolved with h2 of t. And to the LHS we started with x of t convolved with h1 of t plus h2 of t. Hence, it is proved here. So, this is the proof for distributive property. I hope you have understood all three properties, derivation and the proof of that. And before starting the problems on convolution integral, I want you to follow some steps for performing convolution integral operation, how it works. Okay. So, now I will take this heading as convolution integral operation. So, that means when you apply the expression, what are the steps you are supposed to follow to get the end result. Okay. So, it says y of t is equal to what? X of t convolved with h of t. So, that means integral minus infinity to plus infinity x of tau h of t minus tau d tau. Okay. Now, you can go with x of t convolved with h of t or h of t convolved with x of t, applying commutative property. So, whatever the operation you are performing, the steps will be, you will be having two signals, keep one constant and another will vary from one end to another end. That means, another one will be the time shifting one. So, here x of t is considered as the static one and h of t will be the time shifting one. Okay. So, whatever, either you can go with uh, another manner like keeping h of t constant and x of t as a shifting one. Whatever the way you are considering, these steps should be followed. It will makes the getting to the end result easier. So, the first step, in the first step, the impulse response, if you go in this way, x of t x of t convolved with h of t, if you are going like this, in the first step what we have to do, the impulse response h of tau, first it is time reversed to get h of minus tau, and then it is shifted by t to form h of t minus tau. So, that means first we have to plot, considering 0 time shift, first we have to plot h of minus tau, and then we get, so it is better you take the time reversal version of that considering t as 0. So, that will be easiest way to understand the first step. So, next in the second step, the signal x of tau and h of t minus tau, so these two are multiplied together. Why to multiply? For which values we have to multiply? For all values of tau. These two should be multiplied for all values of tau with t fixed at some value. So, we have to multiply all the values of tau together, x of tau and h of t minus tau with the t fixed at some value. Okay, so you will understand this while solving the problem. Let's remember these steps. Okay, next, the product x of tau and h of t minus tau, these two product is integrated over all the values of tau to produce. So what we are producing? A single output value y of t. So that means whenever there is an overlapping region, that value will be integrated with respect to time tau, and that value will be considered as a single output value of y of t. So wherever the overlapping region will be, we get the overlapping region when when another signal is shifting from one end to another end, the overlap region all will be integrated with respect to time, with respect to tau, and each one of them will be considered as a single output value of y of t. So the steps 1, 2, 3 are repeated till the t for different till the complete signal move from one end to another end. Okay, so the one signal is constant, another will be varying from one end to another end. So till the shift signal passes the another signal, the process will be repeating step 1, 2, 3. Okay, so step 4 says repeat step 1 to step 3. Repeat step 1 to step 3. Why? Because t varies from minus infinity to plus infinity to produce entire output y of t. Now, whenever one particular region is producing single output value y of t, the process is repeated till till t varies from minus infinity to plus infinity. So if the process is repeated, the entire output value y of t is obtained. Then we can plot that signal y of t of considering all the single output values that are obtained before. So these are the steps that we have to follow during the convolution integral operation. Okay, so in the next video we'll take some problems on convolution integral. Hope you have understood the steps that we have taken for solving all the properties of convolution integral, commutative, associative, and the distributive properties. If you have any queries, do reply or comment in the video. Thank you.